Okay, welcome back everyone. I hope you enjoyed, those of you who went enjoyed the National Student SIAM Conference in Oxford last week. But this week we're really excited to have Angus here, who's visiting from Oxford. Angus is doing his PhD in Interpretable Deep Learning and Medical Imaging and is going to tell us about it today. So thank you very much.
Hi everyone. So as I already said, I'm going to be talking about Interpretable Deep Learning. Sorry, go to that. I have a problem with how we tend to start talking about interpretability with machine learning and people use it, in that the way lots of people go about choosing to do interpretability is they just kind of use it as an add-on, or kind of just do a nice little side piece to their paper and hey look, now we've got an interpretable model. And so I want to talk about kind of when it comes to using interpretability, what kind of options you have, how you might decide what you think works best for your use case. And then also like actually thinking through what do you want to get out of this rather than doing interpretability for interpretability's sake. So starting with some background and motivation. Deep learning, very briefly, is essentially just a type of machine learning where we do successive layers of mathematical operations. So that could be some kind of neural network where you just have essentially some kind of multiplication, addition, activation function. Could be a transformer model, could be a convolution, but successive layers of mathematical operations which lead to more and more meaningful representations of your data, which you can then do useful classification, regression, so on. Unfortunately, those meaningful representations are meaningful to the model and not to us, so we can't understand them. So interpretability is a very broad definition, but intentionally so, the ability to explain or present in terms understandable to a human. So can we try and understand how some of these models actually work? So I actually have parts of this presentation are interactive. So if you could get your phones out, or if you have a laptop, and go to menti.com and enter the code at the top. And I'm curious to know what you think is a use of interpretability. Like, why would you want to be able to explain how these machine learning models do what they do? And you can put in a few guesses or just one, up to you. And each one, just make them no more than a few words each. So up to you. Don't make it a whole long sentence. If you want to talk about something, just do a few words, like a short phrase. And I really hope this works because it's worked about 50% of the time in practice. Yes, it's working. I'll wait a little bit longer for a few more to come up. Okay, I'm going to start talking about it, even though it's jumping around the place because you're still writing stuff. So debugging, great. I think a couple people wrote that one because it's slightly larger. Yeah, I mean, that's probably one of the first things that like I or engineers think about, because that's what we might want to use it for, because we're trying to create these models. And so we want to try and work out when they get wrong or when they don't. I'm seeing AI safety. So I don't think anyone's actually written specifically this, but like one example of using it for safety would be trying to detect biases. If you can understand why your model's made certain decisions, you can try and find biases within the model and try and either train your model to remove them or like just know what biases exist in your solution that you've got. Uprisings, I'm not sure I quite get that one. Avoid bias, someone did put that. Get feature importance, I guess that's more of a explaining a way of doing interpretability rather than something you want out of it. But all good options, kind of the things that I wrote down, and was curious to see how many you would come up with. Debugging we've talked about, finding biases we've talked about, monitoring models and trying to see when they're not doing what they're meant to be doing anymore, because you can see if the explanations are changing as well as the predictions. Legal obligations, I think, is an interesting one. So GDPR has this right to explanation. When you have a decision made about you, by an automated system, GDPR requires that there's a right to an explanation. They should be able to explain why that decision was made. Or even there's some draft FDA guidance about like medical products and AI stuff saying that they will focus more of their like regulation on algorithms where you cannot explain how they work. So the counter to that is they will regulate the ones you can explain less. That's not what it says. But there's also only draft guidance, so we'll see how that develops. Probably my favorite example of why you might want to use it is scientific discovery. If you have a model which works better than humans and you can understand that model, that means you can learn things from that model. So in what I do with medical applications, if you can get something which does something better than a doctor and you can understand how it does that, then you can then teach the doctor. So that would obviously require a really interpretable model for you to be able to learn something new. In an ideal case where we have a perfectly interpretable model, we understand how it works perfectly, then you can learn things from your data. I think some people kind of alluded to this in their answers, increasing trust, trying to make people more happy with using these algorithms. This is another thing that's a problem with medical imaging. Deep learning's been around for a little bit of a while now. It's being used quite a lot in general business and so on, less so in medical stuff. And maybe part of that reason is because people don't trust it well enough to use it in high-risk scenarios. If we can explain them, maybe people will trust it more, people will use it more, and you can have better outcomes. Or even, and I'm talking about this more later, can you improve user performance? But I'm going to talk more about that one later. So I'm going to talk about a few kind of terms which are important to do with interpretability and explanations. We've got a couple of different types. So one is like a global explanation, where you're describing like general responses of the model. So for example, the model is more likely to predict a zebra if the stripes are there. That's talking about the general case. And then you have a local explanation where it's talking about a specific prediction. So this specific image is a zebra rather than a horse because it's stripy. And different types of methods can do one or both of these, and you need to think about that when you're wanting to use interpretability. Okay, more kind of things to do with interpretability. Post hoc. So this is probably more methods are post hoc, the interpretability by design thing. Post hoc is where you've got your model, say some state-of-the-art model, and you want to explain how it works, just a normal deep learning model. One difficulty with this is it can be difficult to show the explanations are faithful. What I mean by faithful is it can be difficult to show if the explanations are actually what the model's doing. Like you almost have to then explain the explanations and try and show that the explanations are true. Or you have interpretable by design models where actually you just restructure your whole model in the first place to be interpretable. And there's different ways of doing that. I'm going to talk about a couple later. One benefit of this is you've got this inbuilt faithfulness, like the explanations are just how the model works. So therefore you can trust them. But it's less well developed. They're kind of newer. They're not shown to necessarily be state of the art and is as many applications as normal deep learning. So I'm going to go through a few different methods. Most popular one by far is saliency. So sorry, I know your mathematicians is probably like the only equation I have in the entire presentation. But saliency is where you look at the gradient of the logic values, so essentially the output of the network with respect to the pixels. And so it's in words, that's how do I change these pixels to change my output? So you end up with a heat map where the brighter bits of the map say, if you change these pixels, you would change your output prediction. So it's meant to highlight the regions of the image which are more important to the model. And lots of different saliency methods have been come up with. You've got like the raw gradient, which is what I just talked about in that first column. But it can be quite noisy and messy and quite difficult to read. And so these various different methods which have been used to try and improve how it looks, remove some of the noise, make more fine-grained explanations focused on the actual objects. But there's been some problems shown with some of these methods and trying to show that they're faithful and can be used for some of the reasons people want to use interpretability. So we have another Menti. If you still have it up, it should just load the next question. If it doesn't, then put the code in again. What we've got here is Adebayo et al. Did some experiments where they randomized weights of a network. So they trained a network to do classification of different, say in this case, birds, really well. And then they took one of the layers of the network and randomized the weights in it. So now you have a network which is useless because you randomize one of the layers, you end up with essentially useless output. It's just as good as random guessing which bird it's going to be. And then they use these saliency methods to try and explain both the fully trained model and the model where you've randomized a section of it. So you have one model which is really good and one model which is really bad. You would expect different explanations from those two models. One of these rows at the bottom is for a randomized model, and one of the rows is for the fully trained model. Which one do you think is the randomized model? I believe this will ask you to guess either the top row or the bottom row. Which one do you think is from the random model? You have 6 more seconds. Ah, cool. That proves the point perfectly. You were split evenly about which one you thought it might be, right? So you can't really tell the difference between the model that was really good and the model that is essentially random. So there's something that's a little worrying for an explanation method is maybe wanting to help us debug, for example. If there's no link between the model's outcome and behavior to the explanation you're getting, how can you use it to debug your system? I also have some other issues with saliency. So saliency does work sometimes. I'm not saying it doesn't work all the time. Go read the paper for details. That wasn't mine, but for example, GradCAM, I think it's great, but it's an incomplete explanation. It's only partial, right? It tells you which region of the image is important, but it doesn't tell you why. So in the examples I've got on the right side of the screen there, in that bottom example, there's a really bright bit by the edge of the skull. What about it's important? Is it the skull? Is it the shape of the skull? Is it the thickness? Is it how bright it is? Is it actually the dark patch just next to it? I've got no idea. I just know that that region was important. So it's not a complete explanation, even though it's better than nothing, right? So what other ways might we try and create explanations? Rather than trying to use raw pixels, can we use anything else? So one example is using concepts. So can we use semantically meaningful concepts? So for example, the zebra is a zebra because it's stripy. So that concept there is the concept of stripiness. Or this lung nodule is malignant because it's large and it's spiculated. So the concept could be the size and whether it's spiculated or not, which is like something to do with texture of the nodule. And this is really good because it puts explanations in terms that people are already familiar with rather than just raw pixels. But how might we go and try and do it? So here's a few different examples. And throughout all of this, I'm not showing everything. There's other options. I'm just showing some examples. You could do a concept bottleneck where you just predict the concepts as an intermediate step, and then you predict your thing you're interested in from those concepts. So now you don't understand how it learned the concepts, but you do know how it goes from concept to outcome. So you could say, hey, this is this type of bird because it has this wing color, this beak length, this undertail color, and so on. That requires a lot of labeled data though, because you need that labeled data for every single image you've got. So one other option, and what I quite like, is testing with concept activation vectors, or TCAV for short, where this is a model you can use post hoc, so it's not an interpretable model. Sorry, not interpretable by design model. You can use it on any normal deep learning network, and you learn meaningful directions in the activation space. So you kind of input example images of your concepts and other random images and try and look at how those are encoded in the activation space of your network and learn a vector which now represents your concept. And now this vector is what you use in place of your concept, and you kind of look at how the model reacts to that vector, and you can understand, there's a lot more detail going on, but you can look at how the concepts work for a fully trained normal neural network without changing the network at all. Or you have concept whitening, which is I kind of see it as somewhere in between these two, where you do use these labels during training, but you don't need them for the whole data set. And you just kind of encourage your model to treat the concepts as separately as possible, to try and disentangle them. So it doesn't, in activation space, it has this very clear direction, which we can look at, means the type of beak. This very clear direction means the wing color. But it can still learn all these other concepts which we haven't necessarily included. So it could be a more powerful model. Another thing we could do is use examples. So can we use example images as our explanation? This kind of, you can imagine this in two different ways. You've got counterfactuals where you say, you think of another scenario. So what do I need to change about this dog image to be predicted a cat instead? Oh, if you just made the ears a bit pointy, it would be a cat. Or case-based, where you could say, this is a dog because here's 5 images which it's similar to, and they're all dogs. And so your explanation there is just the images that are similar to your test image. And so once again, here are some examples. So you've got that thing I just described, where you've got deep K nearest neighbors, where you use a deep learning model and the activations within that model. And you just look at the K nearest images in activation space to your test image, and hey, look, this panda, they're all pandas, so therefore it's going to be a panda. And the ones that aren't like it are buses, so therefore it's not a bus. And there's some more complex maths in there to try and give some kind of confidence to that estimate rather than just a yes, it's a panda. But once again, go read the paper for details. Or you have something like proto-PNet or prototypical part network, which learns prototypical parts of training images, so small subparts of training images, which represent each class. And so in this example, it's learned that, where's my mouse gone? It's learned that this orange part of this bird is useful, and so it will compare it to every image it's seen, and same with this green part and same with this blue part. And the way you'd read this explanation is you'd say, oh, it's predicting this bird because the belly looks like this belly I've seen before, and the wing looks like this wing I've seen before, and the head looks like this head I've seen before. And that's why I predicted the class I predicted. For a counterfactual example, and this is kind of not as advanced and is generally used for simpler data sets. But let me just minimize that. But we've got an example here where you've got MNIST, just handwritten digits, and you've got a counterfactual where we've got a 4, and what do we need to change about this image to make it a 9? What do we need to change about this image to make it a 1? Or do we need to change about this 5 to make it an 8? And this method generates some counterfactuals to show you what the minimum change to do that would be. And that frankly is very related to saliency because it looks at that gradient and kind of perturbs the pixels with the highest gradient. Okay, cool. Now I'm going to be going through some example methods and kind of how some of this fits together. But why are you using it? What's the point? So when you're using interpretability, you need to think about what you want out of it, and quite importantly, who is going to be using it. So especially when you think about medical side of things. So for example, you might have an engineer debugging the model, and they're going to want different things from if a clinician is working in practice and they're using this machine learning model as some kind of risk score, and there's an explanation for it. They're going to want different things from what the engineer is going to want. And same thing with maybe a patient's being using something and they're told they've got some kind of disease, they're going to want a different kind of explanation from the doctor because they understand different things. So as an example, what you might want for the engineer is it can be really technical, it can be really detailed. They want as much information as they can to try and improve the model development. You want global explanations to try and understand general trends, but you also want to have local explanations because you want to understand for this specific outlier, why did it get it wrong? Like what's going wrong with these sets of images? You can find out by looking at specific examples. Quiz time. What do you think would be important for important properties for an explanation to have for a clinician who is diagnosing lung cancer using some kind of risk score to help them do that. So they've got an image, they're diagnosing cancer from it, and they get a machine learning model saying, hey, this person's score risk is 8 out of 10. What kind of explanation might be useful related to that? And we can talk about some of the properties that I might have talked about on the last slide or previously. And please work. If it doesn't, I got the answers on the next slide. Has anyone submitted anything? Yes, good. Just wait a little bit longer. Okay, we'll start talking about these ones. So a few things people have mentioned here are different property, not necessarily properties of the explanation, but different things they might want in the explanation. So they might want to know the size or the location, right? And that's specific to the problem at hand. So you're going to need to ask the clinicians, what things are they going to want out of this solution? Is it important for you to know size? Is it important for you to know whether it's speculated? Is it important for you to know this? And does your explanation help with that, or is that just actually going to be some other solution and your explanations are something separate? Simplicity is also a good point. It can be technical but needs to be in doctor speak rather than in engineering speak, right? The concepts a clinician understands are different from a concept say engineer understands, and so you need to make sure they're adapted towards them. So in regards to that, for example, even different clinicians, so you might have a radiographer or an oncologist, even they speak slightly different languages or have different opinions about the most useful things to show them. And so you need to think about exactly what type of doctor, rather than just doctors in general, that you're going to be showing this to. You also have to make sure it actually fits with their current workflow. It doesn't matter how great your model is, if it doesn't work with how they do their job, then it's never going to get used anyway. In regards to global and local, yeah, okay, global can give a general understanding of how this model works, but I would say a clinician really would like to have a local explanation as well, because they want to explain to a specific patient why they're telling them they have cancer or not, right? They want to be able to say, they don't want to say computer says no. They want to be able to explain for a specific prediction, right? All right, and this is me being a bit mean about some of the research space. You've written a paper in medical imaging, and you've used some cool ResNet to do some cool classification task, and the reviewer has gone, hey, why haven't you done anything interpretable? You should be interpretable. This is a high-risk problem. It's patients' lives are at risk. And so you go, oh, great, okay. Look, I've been interpretable now. Thanks, accept my paper. What conclusions can we draw from these images? What could you say about how the model works, or frankly anything about them? I would argue none. You can't make any conclusions from this. You can't say, oh, the model tends to look in the head, because you don't have no evidence to back that up. You've got 4 images. You don't have a whole data set. If you wanted to show whether it tended to look inside the head or not, then you should do some analysis where you segment the head and you do this kind of heat map on the whole data set, and then look at how often that overlaps with the segmentation of the head. And then you could provide a number, a quantitative value of how often it looks inside the head as opposed to outside the head. This doesn't tell you that. You can't say, oh, it's looking at this specific concept. You can't, like it. Yeah, I don't like it. And I see it a lot in different medical imaging papers of people just throw in some saliency just to say, hey, look, now it's interpretable. You need to think about what actual conclusions or hypotheses you can show by doing this interpretability rather than just throwing it in for interpretability's sake. Okay, measuring interpretability. I've kind of talked about an example just a moment ago. You might want to measure whether it's inside or outside the head or whatever, right? There's two different types of metrics we will talk about. You've got functionally grounded, where we don't have any humans, we just do some kind of automated metric that we can use. One example of this might be like sparsity, how simple the explanation is, or how small it is, which you can calculate without humans. That's great, because humans are annoying and expensive. You have human-grounded explanations where you do use real humans, but you might use a simplified task rather than your real task that you want to use in the end. So which of these two explanations do you prefer, for example? It would be an example of a human-grounded metric. Application-grounded, where we actually use the real humans and the real tasks and see how the explanations actually affect them doing this task. So the first two aspects, the first two types of these measurements can measure aspects of interpretability, I've already mentioned, like sparsity, or it could measure like trustworthiness. But only application-grounded metrics can actually see whether it improves performance or changes performance in the task you're trying to do. So, for example, we're currently doing a study called the AGE study, the Algorithmic Gestational Age Estimation Study. Literally recruitment emails sent out today. And we want to explore how explanations can affect a clinician's estimate in estimating gestational age, but I'll get onto the data set in a moment. We've kind of got three things I want to talk about in terms of the interpretability side of the study. We want clinical utility, like can the explanations actually improve the clinician at performing the task? Cool, I just do the accuracies, does the accuracy of the clinician change when they have the explanations compared to when they don't? Trust, so we're actually asking the clinician to give an estimate on their confidence, on how confident they are in providing their estimate. And we're doing that both with and without the explanation. So we can see how that changes. And also some self-report mistrust in the model. So we can see whether their general opinion about the model changes. Obviously, it's only qualitative, it's difficult to show, but you can still ask, right? It's better than nothing. We can also see agreement. So we can actually look at the regions the model tends to look at, and we can look at the regions the clinician tends to look at, because we're asking them, which regions did you use to make this prediction? And we can see, does the clinician tend to use the same region of the image as the model? So how is this study actually set up? We've got a data set called the Fetal Growth Longitudinal Study in the Intergrowth 21st data set, which is a data set of fetal ultrasound brains across the whole range of gestational age, from, well, not the whole range, from a range of gestational age from 13 to 42 weeks. So gestational age is just how old the fetus is. And this is the data set we trained our model on. We had around 120,000 images. The interpretability method we're using is something called Proto-PNet, which I mentioned previously, where it learns regions of the training images which kind of it represents that class with. So I'll explain how that works here. You have some kind of convolutional neural network, which you create a set of feature maps or a representation of your data. And then we have a set of prototypes. So prototypes are just vectors of the same length as the number of maps you have. So the feature maps are dimensioned height by width by depth. The prototypes are just a vector of length d for depth. And they are essentially a part of a training image that it's seen previously at some point during training. And it will compare the feature map for your test image with each of these vectors and generate a similarity heat map for those. So that's what this is. So we end up with this heat map shows how similar this prototype is to each region of this test image. We can then just do a max pool operation, pass it for a fully connected layer, and you end up with your predictions. So the model essentially works by comparing the similarity of your prototype with your test image, or various different prototypes. So for an example explanation looks something like this. So the different prototypes just shown in this column here, and you read this prototype, you'd read this explanation with this looks like that. So this part of this training image looks like this part of the test image, and that's why I predicted the class I predicted. The heat maps are essentially the exact same thing as what the yellow boxes are showing, just the yellow boxes are a simplification. The yellow boxes are simply drawn around most of the heat map. That's how we create them. I'm just going to skip that one. So the study is composed of 3 different parts, 3 different stages. We asked the clinician to estimate gestational age with just the image. Then we asked them to estimate it with the image and the prediction from our algorithm. And then we asked them to do it one third and final time with the prediction from the algorithm and with an explanation for that prediction. So we can see how each of these components improve or not improve their performance. In stage 1, we also asked the clinician to give us a load of features that they think influence their estimate, because then we can compare those features with what the model says it's using. So just an example of what the software looks like. We've got various different questions at the top. The clinician can highlight regions they found important and say how confident they were in their estimate. And then stage 2 is very similar, but now they have an estimate at the top of the image, which we provide them. And then finally stage 3, where they also have the explanation there on the side. So we've got some preliminary results where we just did this with one clinician just to see if it worked. And we've actually received ethics approval to do the full study now, and so we've sent out recruitment emails to hopefully get around 30 more participants to do this study. What this one clinician had was, in that top right, we have mean average error on the y-axis, and on the x-axis we have different stages of the study. So the image is that first stage where they just had the image, and they got an average error of 23 days. With the algorithm's help, they got an average error of 9.2 days. And then with the explanations as well, they got an average error of 8.6 days. So we can say that for this specific clinician, the algorithm helped them a lot, and the explanations helped them a little bit. So we can't be conclusive about any results because it's just one clinician. We need to see how that, like in general, clinicians are affected by these. But it's an interesting start. As I said previously, we also get all these different features that the clinician said was important, and that will be really useful for both comparing to this explanation method, and in the future, if we use different explanation methods on the same data set, we can compare the features that the clinician said are important with whatever that explanation method says. How long have I got? Not very long. All right, so decisions. There are various decisions we had to make about the study. One of them was how many prototypes to show. So there's actually, the model has like 65 prototypes, or actually, I can't remember exactly, around that magnitude of prototypes. If we were to show them all, it's not all going to fit on one screen because you need one row prototype. So you can only show so many. We settled on 4. Why did we settle on 4? And if there's 60 prototypes, then if you're only showing 4 out of 60, doesn't that mean you're not really showing the full explanation? You're only showing one tiny part of the explanation. So are you just lying? We did some really simple pruning where we looked at that weight of that finely fully connected layer. And if it was below a value, we set it to 0. If it was above a value, we kept it. And you have to tune that value. And because of that, we could massively reduce the number of prototypes which were relevant to the prediction and adjust how much of the explanation we could show with only 4 prototypes. So in this figure on the right, we have on the y-axis explanation completeness, which is essentially the proportion of the output that's explained by the number of prototypes that you're displaying on the screen. So on the x-axis is the number of prototypes that you might be displaying. So we've drawn a dashed line of 4, which is the number of prototypes we're displaying in the study. On the unpruned model, the blue line, you get around 40% of the explanation is actually shown on the screen. On a heavily pruned model, which is the green line, we can get 80% of the explanation. So double the explanation on the screen. And the green line is actually the one we ended up going with. It has slightly worse performance, so the average error went to 7.5 days as opposed to 6.7 days. But you're far more truthful with your explanations in showing them to clinicians. Time is money. We can only get so much clinician time. It was really important. We've got 120,000 images. I can't show 120,000 images to the clinicians. I have to show less than 120,000. We went with 65 because we did a little practice study and we timed everything and saw what was the maximum amount of time we could spend doing each part of the study. And we decided we could take about 2.5 hours of each clinician's time. And so therefore, how many images can we use? Another big decision we had to make was, what do we tell the clinicians about the model? Do we tell them, oh, we've generated this awesome machine learning model, which is really good, and you should listen to what it says, so please do exactly what the machine learning model says? Well, that's really boring, because then they're just going to do what the model says and not think when they do the study. Or maybe they will, I don't know, right? We haven't done that study. Or do we tell them nothing about it? Or do we tell them it's been through standardized tests and performs about as well as a normal clinical scenario? We ended up settling on not telling them very much about the model, but we really had to think about, what are we measuring if we do tell them? What are we measuring if we don't tell them? But if we do tell them, is that realistic in real life? In real life, maybe, because maybe this model's been through some kind of FDA clearance, it's been shown to work in all these studies, and now the clinicians got it and going to be using it, and they trust that it's being used. Or maybe they know nothing about it, and they've just been told, here's a machine learning model, you're starting to use it. Conclusions. There's lots of different ways of using interpretability and many different reasons you might want to use it, but you have to really think about why you want to use it. Don't just use it for interpretability's sake. Think about the specific use case and who is going to be using these models and why you want to have some kind of explanation in the first place. And it's really important to have some kind of method of evaluation. How are you going to measure if you've actually done that thing you want to do with the explanations? We give one example of how you might want to measure clinical utility, so actually improving clinicians' performance by providing them more information with an explanation. And some preliminary results are promising, but we kind of need to do it on more clinicians before we have any conclusive results. I want to thank my two supervisors, Professor Alison Noble and Yaron Gal, and my Health Data Science CDT and UKRR for funding. Any questions?